Hey wonderful listeners, today I'm going to talk about embedding knowledge graphs attentive to positional and centrality qualities. We are from University of Bonn and Fraunhofer EIES working in the Smart Data Analytics group, and I am Afshin Sadri. Knowledge graphs store the information using triples. For example, in the figure here, Bush with the role of president is a triple in this knowledge graph. A triple here can also be represented by a predicate within two entities or a head relation tail. Link prediction over knowledge graphs consists of predicting unknown relations in the knowledge graph. Here in the figure we can see E1 and US might have a relation, but we don't know what. So we formulate this question as if X B lives in, what is Y? In other words, we want to predict a triple consists of Bush as the head, X as the relation, and Y as the tail. Knowledge graph embedding models encode the information of knowledge graphs in the format of vectors or matrices. The only information from the graph that is extracted and used for training of knowledge graph embedding models is the structure of the graph, like just the head relation tail, head relation tail, head relation tail are fed into the models. Most KGE models like TransE, Rotate E, RGCN, and ComGCN are relying on just this structure information. This information is local, which means that we just take one neighborhood of an entity into consideration when training the model. This procedure of training has a challenge in distinguishing of entities when their neighborhood are similar. For example, here in the figure, E1 and E2 have a similar set of neighbors. They are both connected to US, to president, and a university. In the property attentive embeddings, we take into consideration the global properties of entities. This property attentive embeddings can be centrality attentive, which means we learn centrality as a global feature. Centrality indicates the importance of a node inside a graph. For example, in the figure here, we have ranked all the entities based on their degree. Similarly, position attentive embeddings learns the relative position of entities. For example, in the figure here, the distance of E1 and E2 to E3 are different, and this can be used to distinguish E1 and E2. In MDE or previous work, we suggested multi-objective optimization for embeddings. There, we trained together several objectives with independent vectors as formulated here. Each S is an objective function with an independent vector, and W weights are trained together with the objectives. We extend this idea with score functions that train based on different centrality values and positional values. In down left corner of the figure, we see here 4 different centrality values encoded as different weights for each entity, and in the top left we see shortest path to random reference nodes inside the graph, and these are fed into score functions which are aggregated with the other score functions that lend the structural properties of the graph. Then these score functions are aggregated in a one-to-one convolution, and one output is estimated to calculate the loss. We consider 4 types of centrality values in the learning of the model. Beside degree, we included cat centrality, where in this formulation A is an adjacency matrix, alpha is attenuation factor in the range of 0 to 1. We also included page rank, which in this formulation N is the number of vertices and Lj is the degree of node j. We also include the relative eigenvector, in which A is the adjacency matrix. We integrate centrality and distance values into our model by their dedicated score functions in the multi-objective framework. To learn the centralities, the cosine log of the difference in centrality values of two nodes is enforced into the norm to distance of their embedding vectors. For positional information learning, we assume that between any two entity or node in the graph there is an imaginary relation VR. And then we encode this relation with rotation in the 3D space using Euler angles. We also enforce the difference of the cosine of the norm distance of two nodes to a reference node into this formulation. This table presents the evaluation of the model in the link prediction benchmarks WinATRR and FB15K237. We see the improvement of the model over MTE and the state of the art, especially on WinATRR, where the entity number to relation types is much higher than the second dataset. We tested the model over a large biological dataset named as OGBL BOKG. Biological datasets, similar to other graphs in nature, such as social networks and chemical networks, have a large entity to relation type ratio. Here we observe the improvement of the best result by a large margin when comparing Gfa Nn and the previous state of the art. We also evaluated the model with several inductive datasets and compared the results to inductive learning models. Despite that the model was not intended for this task, we observed efficiency of it in the inductive setting as well. In conclusion, we showed that learning the structural information of a network conjointly with the centrality and positional information leads to improvements in the expressiveness of KGEs. A model made on this premise performs highly efficient in link prediction benchmarks in both inductive and transductive settings. And the efficiency improvement based on this method is more significant on networks with a high entity to relation type ratio, like biological, chemical, and social networks. Thank you for your attention. Here is the source code and an email address for questions and inquiries.